Hello there, Mr. Sutton with the AB Calculus 614 Extra Practice Number 1 solutions on volume with known cross-sections. For this problem, we're told the base of a solid is a region enclosed by this parabola and the x-axis here. Cross-sections perpendicular to the x-axis are squares. We want the volume. So let's start by writing an area formula for those cross-sections. In general, we can write a of x equals s squared because we've got squares, so square area. But we have to write this in terms of x. The base of these squares is going to be the distance between these two functions here, between our bounding region functions. So we basically have this upside down parabola and the x-axis. So that's just going to be a distance of this function here, negative x squared plus 4. And we'll be squaring all of that. We also need to find the limits of integration. That's going to be where these two things equal each other. So I'll say negative x squared plus 4 equals 0 at, well, if we add x squared to the other side in square root, we've got plus or minus 2 for those. So our volume then is going to be the integral from negative 2 to positive 2 of this a of x function that we just wrote. And now it's time for the calculator. I'm going to start by putting my area function in my y1 and y equals, just so I don't have to mess around with doing this in an integral. And then quitting out of that, I've got my Math 9 integral here from negative 2 to positive 2 of alpha trace y1 for the area function that I just entered, dx, and that comes out to 34.133. For this problem, the base of a solid is a region enclosed by this upside down parabola and the x-axis here. Cross sections are rectangles with heights twice that of the side in the xy plane. And we're perpendicular to the x-axis, so integrating with respect to x. So let's start by writing the area formula for these rectangles. We can write, in general, a of x equals base times height, because these are rectangles. But now we need to make sure these are both expressed in terms of the base before we can even think about writing all this in terms of x. So they told us that the heights are twice the side in the xy plane. That's basically saying the height is twice the base. So this is really just b times 2b. So that's going to be 2b squared. And now the actual base of these rectangles is just the distance between this function and this function, which is just a distance of negative x squared plus 1. So we have 2 times this distance squared. That's what we'll put in for our function to integrate. But now we also have to find the limits of integration. That's going to be where negative x squared plus 1 equals 0. That's our limits of our bounded region. And if we add x squared to the other side and square root, we get x equals plus or minus 1. So for my volume, I need the integral from negative 1 to positive 1 of this a of x function I just wrote, dx. And now let me go to the calculator. To minimize the chance of making mistakes, I'm going to do most of my work in the y equals. So for y1, I've just put in this negative x squared plus 1 function. In my y2, I write the actual area function. This is going to be 2 times this stuff squared. And then let me quit out of there and get an integral. So I do Math 9, and I've got the integral from negative 1 to positive 1, alpha trace y2, because that's where I put my area function, and dx gives me a volume of 2.133. On this problem, we have the base of a solid enclosed by this upside down parabola and the x-axis, with cross sections to the x-axis being semicircles. All right, well, let me, if I want to find the volume of this, I need to first find the area of these semicircular cross sections. So in general, we can write area is 1/2 pi r squared, half the area of a regular circle. And to express this in terms of x, let me figure out what my r is going to be. So the diameter of these semicircles is the distance between these two functions, so essentially negative x squared plus 4, because you're just subtracting 0 to find that distance. But the radius is half the diameter. So we actually need all this stuff divided by 2 to fill in for my radius here. So I'm going to write 1/2 pi times 1/2 of this function up here. And then all of that stuff, the 1/2 and all this stuff, it's all being squared. Because to square the radius, I have to square half the diameter. Now let me find my limits of integration. That's going to be where negative x squared plus 4 equals 0. If I add x squared over here and square root both sides. I've got x equals plus or minus 2 as my limits of integration. So for my volume, I've got the integral from negative 2 to positive 2 of this a of x formula I just wrote with a little dx after. And let me put this in the calculator now. So I'm going to do a whole bunch of work in the y equals and then not a whole lot of work on the main screen when I actually call up my integral function. For my y1, I've actually entered the radius in here, 1/2 of negative x squared plus 4. This whole y1 is just my radius. So now when I actually write out my area formula in y2, I can just do 1/2 pi times y1 squared because I'm just squaring the radius. And now I don't have to worry about parentheses within parentheses. All right, let me quit out of there and do math 9 for my integral. We're going from negative 2 to positive 2 for this. And I'm going to do alpha trace y2 for my area function, dx, and that all comes out to 13.404. On this problem, base of a solid is the region enclosed by this semicircle here and the x-axis. Cross-sections perpendicular to the x-axis are isosceles right triangles, one leg in the xy plane. So let me start by writing, if I want the volume of this, let me start by writing the area of my cross-sections in terms of x. So I can write a of x in general equals 1/2 base times height. But since these triangles are isosceles, and we have one leg in the xy plane, and obviously then the other leg must be sticking straight up and forming our height, this is really just 1/2 base times base, so 1/2 base squared. Now the base is just going to be the distance between the semicircle and the x-axis, which is just this semicircle formula. It says y equals, so we have the height of the semicircle right here. So that's going to just be 1/2 times all this stuff squared. Now let me find my limits of integration. So I'm going to have, let's see here, this whole thing equals 0 at positive 5 and negative 5, we can see. So I've got volume being the integral from negative 5 to positive 5 of this a of x that I just wrote, dx. Now it's time for the calculator. So I'm going to put some things in my y equals just to make my life a little easier. In y1, I'm putting this semicircle formula. And in y2, I'm actually putting the area formula, 1/2 times this stuff squared. Now let me quit out of there and do math 9 for my integral. We're going from negative 5 to positive 5. We're doing alpha trace y2 because that's where I stuck my area formula. And then dx. Press enter. This comes out to 83.333. For this problem, base of a solid is the region enclosed by this exponential function, both axes, and this vertical line. If planes, cross-sections perpendicular to the x-axis are squares, what's the volume? So let's start by getting the area formula for our cross-section, our squares. So in general, that's going to be a of x equals s squared. Now let's express this in terms of x. And for that, we kind of need a visual of this, but it's a no graphing problem. So just kind of trying to picture what's going on. Y equals e to the negative x. That's a decaying exponential function. It's going down, but never crosses the x-axis. And we also have the line x equals 3 kind of stopping where that area is going. So our distance, our base of our squares, is just going to be the distance from this function to the x-axis, which is just the function itself, e to the negative x. So we can just write e to the negative x squared, and we're actually going to simplify this when we put it inside the integral. So now for that integral, we've got the volume being the integral from where to where? Well, we're starting at the y-axis. So we're going from 0 to this vertical line at x equals 3. So from 0 to 3, and inside here I'm going to simplify this now to be e to the negative 2x dx. And again, this is a no calculator problem, so we're going to do this by hand. Antiderivative of e to the negative 2x, that's going to be e to the negative 2x divided by my tail of negative 2 to offset the chain rule. So that's actually negative 1/2 e to the negative 2x, evaluated from 0 to 3. I'm going to pull this negative 1/2 out of here, and inside I'll just do this stuff with 3 plugged in minus this stuff with 0 plugged in. So e to the negative 2 times 3 minus e to the negative 2 times 0. we have to go a little further. Our answers here are all simplified in the answer choices. So this is e to the negative 6 minus, this is just going to be 1 because e to the 0 is 1. And I can go just a little bit further with this one. If I'm doing a negative times all this stuff, I could rewrite this as 1 minus e to the negative 6. And all of this is going to be over 2. So 1 minus e to the negative 6 over 2 gives us answer choice A. For this problem, the base of a loudspeaker is determined by these two curves, and they actually gave us a graph of this. And this is just between 1 and 4. So for this loudspeaker, we're told cross-sections perpendicular to the x-axis are squares. They even give us the 3D image here, so they really pulled out all the stops on this one. Based on this, we want the volume of the loudspeaker in cubic units. Not that the units matter because it's multiple choice, but for what it's worth. Okay, so we need to get the area of the cross-sections here, the area of these squares. I'm going to write a of x equals s squared because they're squares. But now we need to actually express this in terms of x. So the squares, the bases of these squares, are the distances as you go from the top function down to the bottom function here. So we can just write, instead of s squared, we can write x squared over 10 minus negative x squared over 10, or x squared over 10 plus x squared over 10. Basically, just getting the distance from here down to here by subtracting. And that's all going to be squared. So I'll put this in my calculator, and I'll clean this up a little bit in my calculator. But now I need to find the limits of integration. Well, actually, they gave those to us, 1 and 4. So our volume then is going to be the integral from 1 to 4 of this a of x that I just wrote out, dx. Now to show you what this looks like on the calculator, I'm going to do most of the work for this problem on the calculator in my y equals. For y1, I've created just this x squared over 10 function because that's kind of the basic unit of what's going on down here. So we basically have then y1 plus y1, or 2y1, being squared. So back on my calculator, I did 2 times y1, whole thing squared. And then quitting out of there, I'll do my integral, so math 9. We're going from 1 to 4. So from 1 to 4 of alpha trace y2 is where I entered my area function, dx. And that comes out to 8.184 exactly. Didn't even have to round off here. So that's going to be choice D. For this problem, base of a solid is the region in the first quadrant bounded by the y-axis, this graph of arctan, horizontal line y equals 3, and a vertical line x equals 1. So that's a lot of bounding things. We're going to want to graph all this out in a minute. For this solid, each cross-section perpendicular to the x-axis is a square. What's the volume? So let's graph everything out now. So first off, I've got arctan in y1. I'll graph my horizontal line y equals 3 in y2. And let me just do zoom 4 just to get a basic sense of what's going on here. So there's arctan. There's my horizontal line. And now I also need a vertical line at 1, and we don't have to draw the x-axis because, well, it's already there. So let me quit out of here, and I'll do second and program to get my vertical line. That's option 4. And we just want a vertical line at x equals 1. So I'll just type 1, press enter. There we go. This is the region in between these 4 bounding sides that we're trying to revolve, or not revolve. We're trying to get cross sections out of this. So let me just put this on here so we can look at it. So they said that cross sections are going to be squares. So we have a bunch of squares popping out of here, and the base of each square is just the distance between this horizontal line and the arctan function. So let me get my area formula for the squares in general. I'm going to write a of x equals s squared. And now again, the base of the square is this distance here. So instead of s, I'm going to write 3 minus arctan of x. And that's being squared. Now for my volume, that's going to be the integral from 0 to x equals 1 of this a of x formula, dx. And now for the calculator. So I'm actually going to put my area formula in y3 just so I don't have to mess around with putting all this inside an integral. So that's just going to be 3 minus my arctan formula here. And I'm squaring all that. Let me quit out of that now. And we'll do math 9 for the integral. We're going from, we said 0 to 1, so can't ask for an easier integral. alpha trace y3 is where I stored my area formula on this one, dx, and that's all coming out to 6.612, which is going to be choice B. For this calculator-based free response problem, R is this region enclosed by the horizontal line y equals 4, and this polynomial that they gave us here, which we're going to put in our calculator in just a moment. They want us to figure out the volume of the solid generated when R is rotated about the horizontal line y equals 2, or negative 2 rather. So this is kind of spicy for part A, but we'll roll with it. So first thing I'm going to do is actually draw that horizontal line out so I have a visual of what's going on. So that's somewhere down here. And now I'm going to actually enter this in my calculator. I need to figure out limits of integration, so I need to know where the bounded region begins and ends. I'm pretty sure it begins at 0, because if you plug 0 into all of this, you end up with 4. But I want to figure out where else f of x equals 4. So we definitely know f of x equals 4 at x equals 0, but now let's put it in the calculator and get the other intersection. So here we go. I've entered both of these in my y equals. Let me do a zoom 6, because I don't really know how far out I'm going to need to go for these things to cross. Oh, looks like not too far. So let me just set my window between, say, -1 and I don't really want to go much further than 3, because otherwise this thing's growing pretty quickly. So window from -1 to 3, and let me do a zoom fit on this one. And if that doesn't work, I'll just do a zoom 4. So there we go. There's our polynomial. There's our other intersecting line. And let me do second trace intersect. And then let me just move this spider over here. Right there. Enter, enter, enter. That's exactly 2.3 actually. I was going to store it as a constant, but I'm not even going to bother now. So that's just at 2.3. Now that I know where this bounded region begins and ends, I need the area of the cross sections. So since we're revolving this solid around this line down here, we're going to have some space between our bounded region and the axis of revolution. That means we're going to have to use washers, donuts, as our cross-section model, because we're going to have some hollowed out stuff when we revolve this. So I'm going to write my area function, A, and I'm going to write this as A sub 1 actually, because I'm going to write another cross-section area later on in this problem. So A sub 1 equals pi times big R squared minus little r squared. And for big R squared, that's the distance from the further away part of my bounded region to my axis of revolution. So that's a distance of 4 minus -2 that I'm squaring in there. So 4 plus 2 squared, you could write that as. And for my little radius, that's the closer part of the bounded region, minus -2. So we can write this as, they already named it for us. This is f of x plus 2 that's being squared, and all of that subtracted. And at this point, to find the volume, I need to take the integral from 0 to, we said 2.3, of this a of x that I just wrote out, a sub 1 of x dx. Now it's up to the calculator. Just to make my life a little bit easier, I did most of my work in my y equals. For y3, I'm putting my area formula in there. So I have pi times, I'm not going to write 4 plus 2, it's 6. Square that, minus, we've got y1, or f of x plus 2, whole thing squared in there, and close the parentheses. And quitting out of there, I'm again taking the integral from 0 to 2.3. So math 9, 0, 2.3. And I stored my area formula in alpha trace y3 for this one. So dx, that's going to come out to how much? 98.868. There we go. For this part of the problem, they're telling us that region R is the base of a solid, and for this solid, each cross-section perpendicular to the x-axis is an isosceles right triangle with a leg in R. We want the volume. So let's get the area of the cross-sections here. In general, we can say a sub 2 of x equals 1/2 base times height, but we need to be a little more descriptive with our height. Since this is an isosceles triangle with a leg in the xy plane, that means that the leg sticking out of the xy plane, the height, in other words, of these triangles, is going to be the same as the base. It's isosceles, so the two legs are going to be the same. So we can rewrite this as 1/2 base squared. Now to write this in terms of x, the base of these triangles is the distance essentially from this horizontal line to our polynomial here. This distance is just 4 minus f of x. So I'm just going to just write 1/2 parentheses 4 minus f of x, whole thing squared. And now my volume is just going to be the integral from 0 to 2.3, just the bounds of my region. And my integrand is going to be this a sub 2 of x dx. All right, let's plug this in the calculator. So for this one, I'm going back to my y equals, and I'm going to put something in y4 now. I'm going to put my area function in there. This is going to be 1/2 times 4 minus f of x, which again, I've stored f of x in y1, so I don't have to keep rewriting it. And I'm squaring the 4 minus y1 there. Now, quitting out to the main screen, I have this work that I did earlier for part A. I'm just going to yank that input, and I've got the limits of integration that I wanted, 0 to 2.3, but instead of y3, that was the area formula from part A, I'm going to put in a sub 2, which I stored in alpha trace y4 just a second ago. So pretty much the same idea, but a different function that I'm now integrating over the same interval. And enter. That gives us 3.574. For this last part, we're told that there's some vertical line, x equals k, that divides R into two regions of equal area. So I'm just going to draw this out just so we have a visual. They want us to write but not solve an equation involving integrals whose solution gives the value of k. So let's just talk about this area in terms of k. So we can say that the integral from 0 to k of, and how do we get this area? It's just going to be top minus bottom, so 4 minus f of x. So this integral from 0 to k of 4 minus f of x dx has a certain value. What is that value? No idea. But we know that it's equal to the value of this other area over here. So I can write that this equals the integral from k to 2.3 of, well, it's the same functions involved, just 4 minus f of x dx. And they said we didn't have to solve this, so that's it. We're done with this one.